Solar energy is one of the most abundant renewable resources available to us. Solar panels work by converting sunlight into electricity through the photovoltaic effect. When sunlight hits a solar panel, an amazing process begins. Sunlight contains particles of energy called photons. These photons travel from the sun to the solar panel. The solar panel contains semiconductor material, typically made of silicon. Inside this material are electrons that can be excited by the incoming photons. When photons hit the semiconductor material, they transfer their energy to the electrons. These excited electrons create an electric current, which is the flow of electricity. This electricity can then be used to power homes and businesses, making solar energy a clean, renewable resource. And that's the basic principle of how solar energy works, converting sunlight into electricity through the photovoltaic effect. A typical solar panel consists of multiple photovoltaic cells connected together and encased in a protective frame. Let's examine the key components that make up a solar panel. The top layer is a durable glass casing that protects the internal components while allowing sunlight to pass through. Beneath the glass is an anti-reflective coating that maximizes sunlight absorption by reducing reflection. The heart of the panel contains silicon semiconductor layers that are treated to create an electric field. The bottom layer is a backsheet that provides protection against heat dissipation and humidity. The silicon semiconductor consists of two different layers, N-type and P-type silicon. Where these layers meet, they form a p-n junction that creates an electric field. When sunlight hits the solar panel, photons are absorbed by the silicon, energizing electrons. A complete solar panel brings all these components together in a durable frame. The photovoltaic cells are connected in series to achieve the desired voltage output, while the protective layers ensure durability and efficiency in all weather conditions. The panel converts sunlight into electrical energy that flows out as direct current. There are three main types of solar cells used in photovoltaic systems today. These include monocrystalline, polycrystalline, and thin-film solar cells. Let's examine monocrystalline solar cells first. These cells are made from a single, pure silicon crystal. The single crystal structure allows for better electron flow, resulting in higher efficiency between 18 and 24%. These cells are easily recognizable by their uniform black appearance and often have cut corners due to their manufacturing process. While monocrystalline cells are the most efficient option, they also come at the highest cost due to the complex manufacturing process required to create a pure silicon crystal. Polycrystalline solar cells are made from multiple silicon crystals melted together. The crystal boundaries in these cells create some resistance to electron flow, resulting in a slightly lower efficiency range of 15 to 18%. These cells have a distinctive blue speckled appearance due to the way light reflects off the multiple crystal structures. Polycrystalline cells offer a good balance between cost and efficiency, making them a popular choice for residential and commercial installations. Thin-film solar cells use layers of semiconductor materials only micrometers thick. Common materials used include amorphous silicon, cadmium telluride, and copper-indium gallium selenide. These cells have lower efficiency, typically between 10 and 13%, but they use less material and can be manufactured at lower costs. The key advantage of thin-film cells is their flexibility and versatility. They can be applied to curved surfaces and integrated into building materials. Let's compare the three types of solar cells side by side. Monocrystalline cells offer the highest efficiency, but at a premium cost. They're ideal when space is limited and maximum power generation is needed. Polycrystalline cells provide a good balance, making them the most common choice for residential and commercial installations. Thin-film cells sacrifice some efficiency for flexibility and lower cost, making them suitable for specialized applications. The choice between these cell types depends on specific project requirements, budget constraints, and available installation space. Now that we understand the different types of solar cells, let's explore how they connect to the electrical grid. Solar panels generate direct current electricity with electrons flowing in one direction. But most household appliances use alternating current, where electrons periodically reverse direction. Inverters solve this problem by converting the DC electricity from solar panels into AC electricity that can be used in your home. Modern solar systems use three main types of inverters. String inverters are the traditional approach, with one central inverter for the entire system. Microinverters are installed on each individual solar panel, allowing each panel to operate independently. Power optimizers are a hybrid approach, using DC optimizers at each panel with a central string inverter. Each inverter type offers different benefits. Let's compare how they perform in key areas. String inverters are the most affordable option, but they don't handle partial shading well because the entire string is affected. Microinverters provide excellent shade tolerance and panel-level monitoring, but at a higher initial cost. Power optimizers offer a middle ground with excellent performance and monitoring while keeping costs lower than microinverters. Selecting the right inverter type is crucial for maximizing your solar energy system's production and efficiency. Most residential solar systems today are connected to the electrical grid rather than operating completely independently. This connection is managed through an electric meter that can measure electricity flowing in both directions. During sunny days, solar panels often produce more electricity than the home needs at that moment. When panels produce more electricity than needed, the excess is fed back to the grid. This is where net metering comes in. Net metering is a billing mechanism that credits solar energy system owners for the electricity they add to the grid. When solar production is low, such as at night or during cloudy days, the home draws electricity from the grid. The utility company keeps track of the net difference between energy consumed and energy sent back. Homeowners are billed only for their net energy use. This grid connection provides several benefits. Homeowners have reliable power around the clock, they save money through net metering, and they often don't need expensive battery systems for their homes. While off-grid systems do exist, most residential solar installations are grid-connected due to these significant advantages. The grid essentially serves as a large, free battery for solar energy producers. Solar panel efficiency depends on several key factors that must be optimized to generate maximum power. Panel orientation is the direction your solar panels face. In the northern hemisphere, panels should ideally face true south to maximize sun exposure throughout the day. A south-facing orientation ensures the panel receives the most direct sunlight over the course of the day, significantly improving energy production. The tilt angle of your panels should be approximately equal to your location's latitude. This maximizes exposure to the sun's rays throughout the year. Some systems allow seasonal adjustments, steeper angles for winter when the sun is lower, and flatter angles for summer when the sun is higher in the sky. Shading can dramatically reduce solar panel efficiency. Even if only a small portion of a panel is shaded, it can affect the entire system's performance. A small amount of shade can reduce power output by as much as 60%, as cells in a panel are typically connected in series. Modern panels use bypass diodes to mitigate shading effects, allowing current to flow around shaded cells instead of through them. Contrary to what you might expect, solar panels actually become less efficient as they get hotter. Higher temperatures reduce the voltage output of photovoltaic cells. Most panels lose about 0.4% of their efficiency for each degree Celsius above 25 degrees. This is why proper ventilation behind panels is important. Maximum Power Point Tracking, or MPPT, is a technology that helps solar systems operate at peak efficiency regardless of changing environmental conditions. MPPT works by analyzing the current voltage relationship of the panel and finding the maximum power point, the precise voltage and current values that produce the most power. The MPPT controller continuously adjusts the electrical load to maintain this optimal operating point, even as sunlight intensity, temperature, and shading conditions change. MPPT technology can improve overall system efficiency by 20 to 30% compared to systems without it, especially during less than ideal conditions. To optimize your solar panel system, ensure south-facing orientation in the northern hemisphere, set tilt angle equal to your latitude, minimize shading, provide proper ventilation for cooling, and use MPPT technology to maximize power output in all conditions.